Good evening, all of you, and welcome to the Westmont Downtown Series. My name is Bobby Kinnear, and I am the member of the Westmont Foundation Board. And I want you to know that our Westmont Foundation Board and our professors really appreciate you being here. You are in for a very special discussion tonight toward a better vaccine for whooping cough. It's really something, as I said, to see you all, and I want to make sure that you tell all your friends that we're going to be doing this again next year, as we have had the last 8 years. This is the last one for the 2014-2015 series, but not to worry, we're going to be setting up everything for you for next fall, starting in October. So you might have seen these on your chairs. Would you fill them out for me, please? Thank you very much. Because we need your help in deciding what we want to talk about and have conversations about next year, 2015, 2016. So please leave it with Nancy Finney. She's back there with a name tag. And truly, whatever you think you'd like to hear our professors discuss, anything that's important to you globally, locally, personally, we can cover it all. Anyway, I have the honor to introduce Dr. Mark Sargent, the Westmont Provost, and he will in turn introduce our speaker. Dr. Sargent assumed the role of Provost at Westmont College in the spring 2012. A graduate of UCSB, he earned his master's degree and doctorate in English at the Claremont Graduate University, specializing in American literature. He has had a long and distinguished career in higher education. He came to Westmont after 16 years as provost at Gordon College, Massachusetts. Westmont was not new to the family. His wife and his sons graduated from Westmont, and his daughter is at Westmont now. So thank you very much.
Thank you. Thank you, Bobby, and thank you for coming out this evening. It's a real pleasure for me to introduce to you Dr. Steve Julio, who's an associate professor of biology at Westmont. I'm tempted to say that Dr. Julio is someone who is infectious. Well, he is a fine researcher, of course, into infectious diseases. After graduating from Westmont, he earned his doctorate at UCSB. His dissertation described the role of a DNA-modifying enzyme in the virulence of two important human pathogens. One, a relative of the bacterium that causes plague, and another, a causative agent in cholera. He spent 2 years as a researcher at Remedyne, a startup biotech company in the Santa Barbara area here, focused on the development of cancer vaccines. When he returned to UCSB for doctoral studies, he began research on the human respiratory pathogen Bordetella. I assume we'll hear something about that tonight, which causes whooping cough. At Westmont, Dr. Julio has continued his study of the Bordetella pathogen and has engaged students frequently and substantially in his research opportunities. But in another respect, he does have an infectious sense of humor, seen quite often in the practical jokes he can spring on colleagues. Indeed, there's something contagious about his joyful spirit and his congenial manner. Steve has this unique ability to ask really compelling and good questions, but in a way that moves everyone towards creative and hopeful resolutions rather than merely frustration or complaints. And all of these qualities, I think, are some of the reasons why the faculty recently elected him to be the chair of the faculty council and the vice chair of the faculty, which is the highest elected position on the faculty at Westmont College. I know as provost, I'm very much looking forward to working with Steve in his leadership role next year, although I do fear that I will be the subject of a few of those practical jokes. You, of course, have nothing to fear tonight. You have nothing to expect from Dr. Julio other than an engaging, informative presentation about a significant world health issue. So, Steve, thanks for being here. Welcome. So,
Thank you all for coming out. I'm glad to see the University Club put extra chairs in the back for the latecomers, so that's very good to see. And I'm excited that you've come tonight, and I realize that there is a breadth of individuals here, from those who maybe had a career in science to those who don't even really know what science does. And so I'm going to try to tailor my remarks for everyone. And so what I'd like to do today is say that this talk's title is Towards a Better Vaccine for Whooping Cough. That sounds a little bit technical. So really what I want to do is try to understand the need and celebrate the effort towards a better vaccine for whooping cough. And in the midst of that, tell you a little bit about the background and some of the things that researchers are thinking about towards that end. So here is an outline of what I want to discuss with you. First, we'll look at the challenge of infectious diseases and kind of what we face as a society. I'll very briefly tell you about a brief history of vaccines and how they work. We'll talk about whooping cough and the fact that something that was once thought to be a medical afterthought is making a comeback. And then I'll spend some time looking about basic research into vaccine development, and specifically, how can a small liberal arts college actually make a dent or an impact in this effort? And I hope I can convince you of that. So before I begin, let me try to frame the conversation. So I think for many people, you think about there's a problem that involves the natural world, for example, some sort of medical need like a vaccine or an antibiotic, and you think, well, there's some scientific solution that lies on the other end of that, and then there's this area where you think, okay, there's scientists doing something scientific, and they're going to figure out the problem. And maybe for some of you, what it really looks like is this. It's just a big black box, and getting from the problem to the solution is completely unknown. And so what I would like to do tonight is dispel a little bit of that. I want to fill in some of the information in this box here. For example, what really is at stake, particularly with the disease that I study, which is whooping cough? How do scientists consider the problem? What's their perspective on this? And then what kinds of technical approaches did they take to solve the problem? And I want to tread lightly on the technical aspect. I do want to do a little bit of biology to get you understand exactly what we're doing here. But I think a little biology is good for everybody. So that's the approach that I'll take. Okay, so first, the challenge of infectious diseases. What are we thinking when we talk about infectious diseases? Well, here's the first thing to keep in mind. When we talk about disease, what you really have to know in a broad sense, microorganisms, and I study bacteria, which is a type of microorganisms, they're everywhere in the natural world. So you can find them in soil, you can find them in water, such as the ocean, in a pond. In fact, in this picture right here, you would have bacteria in the water attached to the leaves of these plants. Microorganisms are found everywhere. In fact, in some really extreme environments. You can find microorganisms in these hydrothermal vents, the bottom of the ocean. You can also find them, a couple of years ago, scientists found them in a lake that was buried under some ice in Antarctica. So microorganisms, bacteria in particular, are well adapted everywhere in the world, and as it turns out, of course, the body as well. So you probably are familiar with the fact that your body is a reservoir for bacteria. You probably know in your large intestine, there are many bacteria that help you digest food, amongst other things. You can find them all in your gastrointestinal tract. These are various places. They're also in your respiratory tract, on the surface of your skin, the urogenital tract. Bottom line is, of the cells that are in your body, there are 10 times as many bacteria that live inside or on your body than there are your own cells. So they live in harmony with the body, but there's a caveat to that, of course, and that is some microorganisms, not in particular the ones that live in harmony with the body, but some can cause disease. And so as you know, here's an example of inflammation in the throat, bacteria here that are colonizing the small intestine. Some bacteria are disease-causing. So what do we face when it comes to this type of threat? Well, if you look at infectious disease, just globally, here in the Western world, we're used to thinking of infectious diseases somewhat as a mild problem, and it's just not the case worldwide. So the World Health Organization compiles a report every year, and the last year data were available. Turns out that worldwide, infectious diseases behind cardiovascular disease is the leading cause of death worldwide. And that's just not really all that familiar to our Western ears, because we have the ability, we have the infrastructure, we have the medicine to be able to combat that. But in most of the developing world, infectious diseases are, if not the leading killer. So there is a global imperative to be able to combat these diseases and find solutions for them. So if we take an example, or in this case 2 examples, what do we really mean by the threat to public health for infectious diseases? And these 2 examples are timely because you might know that there has been an Ebola outbreak, and there has been a measles outbreak within the last several months. So as an example, what I want to do is tell you a little bit about what we face and how scientists think how we face threats like this. So if I were to ask you, which of these two bacterial threats, actually they're viral threats, sorry, which of these two viral threats is the most problematic, I would assume that most of you would tell me Ebola, right? And if you actually look at the numbers, that actually might back up that claim. So if you look at the number of cases, the number of deaths, the Ebola outbreak last fall, this is principally obviously in Africa, far outweighs what's happened with the measles virus outbreak, which you might know happened or started at Disneyland here in Southern California, and now it's spread throughout the United States. So those numbers actually belie a little bit of a deeper story that's going on there. So scientists actually like to talk about the reproduction number of a microorganism, a disease-causing microorganism. So what is a reproductive number? It's simply this. If someone has a disease, how many individuals will that infected person pass the disease on to? That's the idea. If you look at Ebola, the number is around 2. And what that means is for a person who has Ebola, on average, under given conditions, that individual will transmit it to 2 other people. Okay? That's what the reproduction number means. For measles, the reproduction number is 18. It's extremely high. Okay? And you would think that doesn't make sense, given these numbers right here. That seems to be the opposite. Well, it has to do with disease characteristics. So it turns out for Ebola, it's just not very transmissible. You actually have to handle bodily fluids from somebody who has Ebola, so you have to be in physical contact with the person. Whereas with measles, you simply have to be in proximity because the virus that causes measles is easily exhaled into the air, can live on surfaces, and someone who is infected with measles can be contagious even before he or she shows symptoms. So you take all of these things together, and it is much, much easier to transmit measles than it is to transmit something like Ebola. Okay? So that begs the question, then why these numbers? And if I tell you that these are numbers from Africa, where there is no vaccine for Ebola, as you might know, these are numbers from the United States, the answer for that is we have a vaccine against measles, right? But if you look at this number right here, 644 cases, that number should be 0. Okay? Measles has effectively been eradicated from the United States since the year 2000. And with this outbreak, this number right here causes great amount of concerns for public health officials. Okay? And the reason for that is because we have dipped below the number that we need for herd immunity, and you've probably heard that term. Herd immunity is the number of individuals who need to be vaccinated or immune so that the disease doesn't spread. And what's happened in recent times, as you've heard in the news, is that our herd immunity has dropped below a level that is effective. And so what happens when an individual from overseas comes to the US, brings the measles virus to Disneyland and spreads it all over the park, pretty soon you have hundreds of cases spreading throughout the United States because of the fact that our herd immunity has dipped below a point and there are susceptible individuals. Okay? So this is a good example that leads me into why we're talking, or what we're talking about tonight, which is whooping cough. So if you look at the reproductive number for whooping cough, it is extremely high, which means that it is amazingly easy to spread the whooping cough bacteria from person to person. So that begs the question and begs the need for effective therapeutics, i.e. a vaccine that can effectively combat that. So that's what I want to spend most of the time talking about here. I want to tell you a little bit about what the vaccine does, how it works, how it doesn't work as well as we think it should, and then what we're doing to try to make inroads towards making a better vaccine. Okay? And then after that, I want to talk for 30 minutes max, and then open it up for questions and discussions that you might have. Okay, so quickly, a brief history of vaccines before we talk about whooping cough in particular. So it turns out that vaccination as a practice has actually been around for probably 1,000 years. Chinese were doing it long, long ago. But the individual who's given credit for inventing, quote unquote, vaccines is Edward Jenner. And here you see him at the turn of the 18th century, inoculating a young boy. And what he noticed is the disease smallpox, which was rampant and epidemic at the time. Milkmaids who actually work with cows, and cows get a related disease called cowpox. Milkmaids never got smallpox. And Jenner thought, there must be something with the cowpox virus, such it's similar enough to smallpox, that the milkmaids working with the cows get the cowpox virus, don't get smallpox. So he actually took a skin lesion from a milkmaid who had cowpox inoculated it into a small boy, and then sometime later actually gave the boy smallpox, actually challenged him with smallpox, which would actually never pass a regulatory body nowadays, obviously. But the boy was fine. Okay, so he's credited with making the first vaccine specifically against the smallpox virus. And really, since then, largely the 20th century has been a century of developing vaccines. And you can look at this list, which I won't go through, but there are many with which you're familiar looking upon that list. And one of the greatest success stories about vaccines actually is smallpox. So 1978 was the last recorded case of a natural smallpox infection in the world. It's been eradicated from the globe. The only place you can find smallpox now is in places in the US and in Russia in research institutions that are tightly regulated, obviously. And so this is the current paradigm for vaccinations for young children from the American Academy of Pediatrics. Again, this list, you can notice some of these that are well familiar, and the regimens of vaccines is meant to protect infants and when you get booster shots, those who are older, over a lifetime from many of the diseases which at one time were a scourge on humanity. So great success stories. So, for example, measles vaccine, which was introduced in the early 1960s. This is a heat map showing for all 50 states, even though only some are listed here, for all 50 states, the number of cases per 1,000 individuals. And the darker the color, the more measles cases. And you can see before the vaccine was introduced, in many cases, after the vaccine was introduced, way fewer cases, almost down to zero, okay, until the last 6 months or so when outbreaks have cropped up over the US. So vaccines have done wonderful things to prevent disease. Okay, measles is a good case in point. So how do they work? So actually, it's quite simple. Even though the science of vaccinology there's somewhat of an art to it, the simplicity with which they work is actually quite compelling. So this slide right here is showing you the fact that you can make a vaccine by taking the bacteria or virus as a disease-causing agent, and you can either inactivate it by killing it, and that can be a vaccine. You can take it and you can tweak it so it doesn't work as well. So it might get into the body just long enough to cause an immune response, but not cause disease. Or what researchers have done, they said, you know what, let's forego the entire organism itself. Let's just take a part of the organism. So all of these things right here are components within the organism that can be used as vaccines. And no matter how you design your vaccine, the idea is this. You take that vaccine, you administer it to the body, and all you're trying to do is get your immune system to respond to it. And so if you can get your immune system to respond properly, so you might have heard of antibodies, which is one way the immune system responds against disease. If you can get your immune system to respond properly to that vaccine, then if you ever see the real thing at some point, your immune system remembers and it knows. It can effectively take care of that infection without you actually getting sick. Okay? So it's quite straightforward the way vaccines work. Now the trick is to actually find the vaccine that successfully does this with the immune system, and that's why vaccinology is as much of an art as it is a science. Okay, so let's look at whooping cough at some level here. So here is whooping cough. It is caused by a bacteria that's called Bordetella. So what you're looking at right here is an electron micrograph. This has been color enhanced, and the pink are the bacteria, and the bacteria are adhering to a cell. This is actually a cell from a rabbit, but Bordetella will infect many organisms, as I'll tell you about momentarily. But Bordetella will stick to cells, and once it does that, it can cause all the nasty things that are associated with the disease whooping cough. Okay? If someone has contracted whooping cough, here's the course of the disease. So for about 7 to 10 days, you simply feel like you have a cold, or maybe a mild flu, nasal congestion, fever, and a mild cough. But then about 10 days after you've picked up the bacteria, that's when the actual symptoms of whooping cough come out in full force. So paroxysmal intense cough, paroxysmal are these bouts of cough, and I'm going to spare you there are videos that you can actually see someone in the throes of a whooping cough. They're quite intense, and you can cough so hard that you can actually crack ribs. So it is the kind of a cough that is the hallmark of the disease, and the name whooping cough comes from the fact that if you're in one of these spasms of coughing, it's hard to catch your breath. And so you try to whoop in air, and you make this whooping sound, and that's where the disease gets its name. It's especially dangerous in infants because it can cause them an aberrant breathing cycle. And so one of the things that is the problem with whooping cough is it actually can be fatal in infants if they're not treated. If you do clear the disease, which most adults will, it will clear within 3 months, give or take, okay? But there's a problem because of the fact that there is significant mortality in infants, and the fact that, as I showed you before, it's a highly effectively transmitted disease. And so the ability to combat whooping cough to protect the most vulnerable is a medical priority. Okay, so what about the bacteria? Where did it come from? How do we get this bacteria that causes diseases in humans so effectively? Well, you got to go a little bit back in the story. So let me tell you the tale of 2 bacteria here rather quickly. So if you go back in time, probably thousands of years, there was a bacteria that is related to the bacteria that causes whooping cough called Bordetella bronchoseptica, kind of a mouthful, okay? Bordetella bronchoseptica has evolved the ability to infect basically everything under the sun, okay? Anything with 4 legs essentially can be infected with Bordetella bronchoseptica. But it has done so in a very wise manner because when it infects any of these animals, it actually doesn't cause a disease. It is non-symptomatic, and the animal carries it basically for its entire life, okay? Pretty good strategy if you're a bacteria. Get into a host, don't cause much of a ruckus, and just live out your existence for the rest of that host life. Pretty good strategy, okay? At some point in the time span of bronchoseptica, probably not more than a few hundred years ago, there were some genetic changes in this bacteria, some mutations, which we're still trying to characterize. But what happened was there was this variant of bronchoseptica called Bordetella pertussis. And Bordetella pertussis, strangely enough, even though it is highly related to this ancestor bacteria, only infects humans. So all of the other organisms that the progenitor bacteria has an easy time infecting, Bordetella pertussis has narrowed its host range to 1, humans, okay? And the disease, as I told you, is vastly different. So it's severely symptomatic and only lasts a few months. And one of the major questions for people who are studying Bordetella is why? How do you have 2 bacteria that are quite similar, if you look at them genetically and biologically, cause greatly different diseases? That's an unknown question and still being researched quite actively, actually. Okay, so you might know that another term for the disease whooping cough is pertussis. And it's called pertussis because that actually is the specific bacteria that causes the whooping cough disease. So those 2 terms are interchangeable when it comes to that human disease. All right, another great vaccine success story. So the vaccine for whooping cough was introduced in the late 1940s. And once that vaccine was introduced, cases of whooping cough dropped to essentially 0, okay? But the problem is, as you might know, in the last 10 to 15 years, for reasons that are still being researched, not fully understood, the cases have risen dramatically. So from a time when the cases were probably in the 1 to 2,000 per year, last year we're up to 28,000 cases of whooping cough, okay, which is cause for great alarm. And that is a drastic increase in the number of cases of a disease that was once well controlled by a vaccine. So another active area of research is, how do we improve this vaccine so that we can combat this dramatic rise in whooping cough cases? Okay, public is well aware of this, as you might know. So it's in the news all the time, outbreaks here and there. There are public address or public campaigns that actually get people vaccinated to be able to combat this disease. You might also know that there have been movements to actually disallow students from enrolling in school unless you've had your vaccination against whooping cough. And in fact, we were just talking earlier today before the lecture, that just today in California, legislation is being considered that would actually not allow individuals to opt out of vaccination for several vaccines, okay? And we can talk about some of the ramifications of that in the Q&A period, because obviously there are implications for saying, yes, you must be vaccinated, versus, wait a second, it's my right not to be vaccinated should I choose. So, you know, there are some clearly political and societal questions in there that need to be fleshed out as well. Okay, so let's now, for the rest of the time, connect this basic research to eventual vaccine development. What are we actually trying to do? All right, So here's where we have to get just a little biological, okay? So I'm going to tap back into, for some of you who maybe haven't had biology for quite some time, tap back into those biological roots from maybe high school or maybe during college, all right? So try to follow along with me here, but I'll keep this fairly basic. So here's what I want you to imagine. I want you to imagine a bacterial cell, okay? And this bacterial cell basically asks itself one simple question: where am I? I told you before at the beginning that bacteria are everywhere on planet Earth, including the body, but that bacteria might be in water somewhere, in the soil, inside a body, and that bacteria has to say, where am I? And it has to get that information to its DNA. Bacteria have DNA, you and I have DNA. We use the same type of information to get things done, and what the bacteria will do is it will express certain genes. Genes are just pieces of DNA. It will express certain genes, and those genes will allow the bacteria to live wherever it finds itself. Okay? So where am I, and what must I do where I find myself? How do they do that physically? Okay, this is about as technical as it gets tonight. All right? Turns out there are small molecular machines inside bacteria. Simple little one-celled organisms, amazing complexity in that single cell of a bacteria. And what these machines do is this. They take the outside information and bring it inside so the bacteria can respond appropriately. So let me take you through how that works. So there's some environment. I'm in the soil. I'm in water somewhere. I'm in someone's respiratory tract. That information is actually sensed by the first molecular machine. And you'll notice that this molecular machine, it's actually a protein. Half of it sticks outside the bacterial cell, and half of it sticks inside the bacterial cell. And that's key, because half the protein actually senses, where am I? And then when it does so, it will actually talk to, quote unquote, the second molecular machine. So these are called two-component regulatory systems, which is a mouthful for two molecular machines getting information from outside the cell, inside the cell. And when that second molecular machine gets activated, it will go and interact with the DNA, and you'll get gene expression that will allow it to, the bacteria, to survive in that environment. Okay, you all with me? Does that make sense? Okay, so what does Bordetella do? Bordetella uses this strategy like many bacteria do. So in Bordetella, it's called BVGAS, for reasons I won't get into, but if you are Bordetella and you find yourself in the respiratory tract, you're going to activate the first part of that two-component regulatory mechanism. It will talk to the second component, which will talk to the DNA, and you'll get the proper gene expression. And I want to mention 3 genes that are important specifically for Bordetella. And they are called FHA, the toxin, and protactin. I'm not even going to tell you what they do. And here's why they're important. They're important because 2 of those, FHA and protactin, color-coded here, stick themselves out on the surface of the bacteria. They're long, sticky fingers, proteins that stick off the surface. Remember that slide, that picture I showed you at the very beginning of the bacteria sticking to cells? Here's how they do it. So the bacteria says, I'm in the respiratory tract. Time to be able to stick to cells in the respiratory tract. I need to get these sticky appendages outside on myself so I can stick to cells. And so that's how it does it, because it now knows it's in the respiratory tract. Okay? And this toxin is a third protein that just gets excreted away from the cell and can go do nasty things to other host cells inside your body. We actually still don't know exactly what the toxin does, but it can damage cells. Okay, so why these 3? These 3 because this is how the vaccine works. So let's compare a natural infection to the vaccine. So this is just what I showed you on the previous slide. This is part of the bacteria expressing these proteins now that it's in the respiratory tract. Okay? What we know is this. We know that the immune response inside the human body says, I see that, I see that, and I see that. And when it does that successfully, it will be able to get rid of the infection, clears the infection, and it remembers so that you are protected against subsequent disease. That's the way the immune system works when it's doing its job. And it turns out, through many years of research, we've determined that these 3 components, these 3 proteins, are involved in the immune response. So someone had a pretty good idea, and they said, well, if the immune system recognizes those proteins, let's just make a vaccine using them. So the current vaccine for whooping cough actually is these 3 proteins, FHA, toxin, and protectin. Okay? That's the component of the vaccine. And it works in the same exact way. The immune system, when these proteins are administered to the body, when you're immunized, there's an immune response against those proteins, and the immune system doesn't care if it sees the intact whole bacteria. All it needs is the parts of the bacteria that it makes an immune response to. And that's what happens right here. And so you're protected against disease. Okay? And that's the way the vaccine works against whooping cough. Okay, now you might think, great, so end of story. It's all said and done. Well, that's not the end of story. Actually, the current vaccines, actually, I just mentioned, one is the one that's given to young children starting at 2 months, and you might know there's a booster shot that's given at age 12 in the teenage years, and they're both made on this paradigm right here. Okay, so go back a little bit. The vaccine I just told you about, made from those components, has only been around since about the mid-1990s, but I told you the vaccine was actually developed in the 1940s. So from 1940s till mid-1990s, the vaccine actually was the entire bacterial cell, and they just killed it. It was a killed vaccine. So it can't cause disease, but administered to the body, and the immune system says, oh, I see some proteins there that I can make a response against, and it worked. But the advantages of that vaccine that used to be used was it's safe, and it prevented colonization. But there was one big issue. It was reactogenic, which means it caused a lot of side effects, especially in infants. High fevers, babies were really fussy, and so parents didn't appreciate nor enjoy seeing their children have a reaction to the vaccine that was mild, but yet nonetheless very uncomfortable. And so the so-called acellular vaccine, the one I just told you about, was developed for that. Okay? And the great thing about the acellular vaccine is that it's safe and it is well tolerated. Almost no side effects in those that get the vaccine. Much, much, much more mild than the whole cell one that was used for decades previous. Okay? But, you knew there was a but coming here, it has a limited effectiveness. So whereas the whole cell kill is actually quite effective at having long-term immunization against whooping cough, the acellular vaccine lasts several years, which is why you have to get a booster shot when you're about 12 years old. Okay? So advantages and disadvantages to both. And what health professionals have opted for is the acellular vaccine because it does work, albeit shorter term, but the great advantage is it is just much better well tolerated in younger children when they're first getting their vaccinations. Okay? So there is a need for a better vaccine. We would like to be able to say, yes, these work, but they could work better. Okay, so what's Westmont doing? What is my research program doing that might actually contribute to this? And I think there's some exciting things going on. And let me just end my comments here with what we're doing at Westmont that might pave some inroads towards improving this vaccine. Okay, so back to this picture of the bacterial cell and these molecular machines that are saying, yes, here I am in the respiratory tract, and I'm going to get specific gene expression happening so that I can survive in the respiratory tract. Okay? We discovered a second molecular machine system, a second 2-component regulatory system. So it turns out that Bordetella bacteria don't use one of these systems, but they use 2. And so this second one right here is just as important as this first one that I told you about. This first one has been studied, well known for 30 years, and along comes system number 2. And so our job has been to figure out, what is this second system doing? Let me tell you a little bit about what we know. Okay, we do know that it responds to conditions that are found in the respiratory tract, okay, which is what you would expect. But here's the question. When this system gets activated, what types of genes is it activating? I told you about those genes that we've known evokes an immune response. It's part of the current vaccine against whooping cough. Could there be a case here where with this second system that we've discovered, could we discover new proteins, new targets for a vaccine? And I think the answer to that might be yes, okay? And I'm going to show you this, and I'm just going to point something out. These are the kinds of things that scientists who study vaccines and bacteria look at and get really excited. I know this looks like tire treads on the road, okay? But what I'm going to point out is where these two arrows are pointing right here. When we saw that, we said, wow, that is really exciting. Every little black bar you see here is a gene that makes a protein from Bordetella. And where those two arrows are pointing are exciting to us because what it's saying is that in this first system, I told you, makes those proteins that are used in the vaccine. In our system, we actually have proteins that are brand new, that are recognized by the immune system, made during infection. So these are proteins that have never before been characterized or discovered in Bordetella. And if you want to make a vaccine that's based on genes that are expressed when the bacteria is inside the respiratory tract, and now you have a whole novel or new set of proteins, now we can go and characterize those and ask the question, could they actually, in effect, make a improved, more efficacious, and well-tolerated vaccine? And so that's the direction that we're going in now. And currently, in my lab group at Westmont College, we are trying to make some inroads into how these proteins could eventually be part of a newer and improved and safe whooping cough vaccine. Okay, so if we go back to this paradigm here, here's the problem. Increase in whooping cough cases, and the solution is a better vaccine. And I've showed you a little bit about how we might want to go about doing that. What goes in the box right there? Well, all I've tried to do in brief comments here is to tell you the importance of the medical need, which I hope I've convinced you of, the fact that there is basic research being done so we can understand how the bacteria does what it does. I showed you these molecular machines that tell the bacteria where it is and how it responds appropriately. And then I've told you that actually at Westmont in my lab, we have discovered some novel targets that actually could be useful for improving the vaccine. And that work is still ongoing. That's the story I told you about right there. The way you look at it, that's not where the story ends. Because if, and the if is, will this pan out, then there's a whole host of things that would ever have to happen before you got to your solution. So all of this I'm not going to talk about right now, but I should briefly mention that if a scientist actually comes up with a potential therapy through basic research that has the promise of actually improving an existing therapy, what you need to do is show it's safe, it works well, and that it can be marketed well. And so you have to go through a whole series of experiments with animals. You have to go through clinical trials that the Food and Drug Administration oversees. You have to get extensive regulatory approval for that, manufacturer and quality control, if you pass all of these phases, which finally can lead to a better vaccine. So this is exciting, ongoing. This is several years down the road, should what I told you about today actually pan out, okay? But as a scientist, we get excited about making these discoveries, the potential for using them to improve therapeutics. And one of the great joys that I get to do as part of this is work with an amazing group of students. So all the work I told you about here actually has been done by undergraduate researchers at Westmont College. They're all listed here, and pictures of some of them, those who I have pictures of, are listed here. And this is Callan. She actually got the story going from the beginning. She was the first student who worked with me, and then on down through the years, here are several students. Here's my current students right here. And it has simply been a joy to be able to watch their enthusiasm, their excitement, and their dedication as we kind of partner together and try to work through figuring out how this bacteria does what it does, and hopefully and potentially developing some novel therapeutics towards improving the vaccine. So, thanks for listening. Happy to open it up for discussions and questions.
You had mentioned earlier about the herd immunity level being too low. What is the efficacious level? Is it
Yeah.
98%?
Right, so the question is, so what is a good level of herd immunity? So the benchmark is 95%. So 95% of the population should have a level of immunization that protects them from the disease. In fact, next week at Sansum, they are having the Strive for 95 event, which is several health professionals who are trying to get the word out that this is what we need. If you look at Santa Barbara, and the data are available from public schools, there are some schools that are doing a great job. They are near 100%. There are other schools that are doing a dismal job. They're in the 40s or 50%. And so that's where outbreaks happen. And in fact, last fall, there was an outbreak of whooping cough, 7 students at a local school. The level of immunity there was 50%. And when you get that herd immunity dipping below, it actually causes some problems.
And then I was a little surprised you said the reproduction rate was like a factor of 18
Mhm.
on the measles.
Yes.
And there were 644 cases.
Right.
Somehow led me to believe there would be many more thousands of cases at that level of reproduction.
If there were no immunity, there would be hundreds of thousands of measles cases in the United States right now. But there is a vaccine, and the level of immunity for the measles vaccine is somewhere between 85 and 93%, depending on where you're going. So we are doing a good job with measles vaccine. Had that level been lower, the lower you go, the more cases that we would expect to see. And what you get is actually local pockets of outbreaks. So where you have places where there is low herd immunity, that's where you get your outbreak. So that 644 isn't like a smooth progression of cases. It starts here, you get some cases, start at Disneyland, right? In Texas, there were some. In Minnesota, there were some. Wherever the herd immunity has dipped below the threshold where it's effective. Yeah.
I make the connection right that we discovered these novel proteins, they're just two?
For 2 that are on, yeah, that particular experiment right there.
Recognize that.
Yes.
Yeah, okay. You know anything about their function?
Absolutely nothing. Yeah. So we would there are ways of actually physically extracting those black bars from that gel.
My next question was how do you purify it?
Yeah. Well, actually, you actually physically cut them out of that gel, and then you can actually subject it to mass spectrometry and actually get the protein amino acid sequence. Will be the way that we would do it, which we would have to collaborate with because we don't have that instrument at Westmont, but it would be easy enough to actually do. So certainly on the dock. to do.
The first set of 3 antigens
Mhm.
you talked about.
Right.
How are they prepared? They just like homogenize some bacteria and then do an extraction to purify it?
Excellent question. All 3 of those, so I showed you one that gets excreted, exported away from the cell. It turns out all 3 of them are. So for the other 2, part of the protein sticks in the bacteria, but other parts of the protein get excreted from the cell. So they grow up large batches of Bordetella, they spin down the bacteria, they take the supernatant or the liquid that results, and there you have your proteins. Yeah. Sir.
You mentioned that the whooping cough incident level is going up over the last, I don't know, what, 10 or 15 years. Is that due to the vaccination rate going down, or is
Yes.
there something going on with the organism itself that it's mutating and becoming different?
Most assuredly both. Yes, so certainly immunization levels aren't where they need to be, number one. But there have been some studies done that have shown that the bacteria that are circulating amongst people who are getting infected is actually genetically different than samples that have been frozen away from those who had pertussis even 15, 20 years ago. And that's just a response to the vaccine. And so one component that used to be in the vaccine no longer is, because some of the bacteria that are circulating in the environment no longer make that protein. So in a sense, the bacteria learned, I'm not going to make that protein anymore because if I do, I'm going to get killed by the immune system. So it's always an arms race, right? We're wise and smart, we figure out some deal, but bacteria are pretty smart too, and they figure out a way around it. And then we have to figure out something else. And so it's kind of this arms race between our wits and the bacteria's ability to outsmart us. So,
Does that happen in other
absolutely, yeah, yeah.
organisms that we have vaccines for?
Mhm.
Is that
Yeah.
also happening?
Not as prevalent, but when you dip that herd immunity low, you allow for that to happen much more easily. Yeah. Yes, Steve.
With those that had the vaccination, say in the post-1990s, I'm thinking of my kids, would their docs know that they need to get booster shots?
Yes.
Or what, is there a protocol that's known?
Yeah, that's the current regimen. Is so if you have received what's called the acellular vaccine, which is those 3 protein components, that booster is required about every 7 to 10 years, give or take, depending on. Yep.
So we should still be getting shots like that every month?
You know, if you want to keep herd immunity up, yeah, you should. Yep.
Even if you got that whole cell or that other one?
The whole cell is much longer lasting than the acellular. I don't know if it's lifelong protection. I'm actually not exactly sure on those data, but it certainly is much more long lasting than is the acellular vaccine.
What kind of research is being done to help those who don't trust the vaccines, help them understand why they should trust the vaccine?
Right.
How can
That's
you prove it to them?
Yeah, that's the million-dollar question. So the question is, how can you encourage those who distrust the vaccine or just the vaccination process to understand that this actually is a not only medical necessity, but a societal imperative? So there have been studies done that have tried to figure out the best way to do that, and here's one way that doesn't work: information overload. So they actually have done, there's a study at Dartmouth that was done last year that found that if you try and convince someone who is already convinced that vaccinations are harmful with information that is contrary to their beliefs, they double down. They're actually even more resolved. So the information campaign simply doesn't work. So the current problem is that we have two groups of people who are screaming at each other, and sometimes literally. And so you have the people who don't trust vaccinations for various reasons, saying, I will not vaccinate my child. And you have health professionals and those who are saying vaccines are important, if not critical, and you must vaccinate your child, not just for your child's health, but for the health of those around that child. And you have these two camps that are just screaming at each other. And what I'm convinced, and I have no data for this, obviously, but I'm convinced it's going to come to someone that's going to be a health professional, that person's primary care physician, the small child's pediatrician, who is going to have a level of wisdom and tact and compassion to listen to the person, understand their fears, and not legitimize them, but try to help them understand that those fears really have no basis in fact. So if I were to talk to someone, and I have talked to people who don't trust the whole vaccination program, the first thing I say is, I understand that actually you and I, or group 1 and group 2, we have the same goal. We want to protect our kids. And we just have different ideas about how to do that. And the data are overwhelming that vaccines are safe. It doesn't mean that in every single case a vaccine can't cause harm, right? But overwhelmingly, vaccines have been proven to be safe. Study after study after study, hundreds of thousands of individuals' data have been looked at. So it's just going to be the kind of effort that is going to be personal rather than trying to get the information out en masse or convince one group via mass campaign from another group, because that just simply hasn't been working. And in fact, it could be, according to the study from Dartmouth, actually detrimental to the cause. But it's very difficult, right? Because there's issues wrapped up in that go beyond vaccination. Personal autonomy, right? Which is a hallmark of our American culture. And so, you will not tell me what to do. And if I don't want to vaccinate my child, I will not vaccinate my child. And so here comes the controversy with what California is considering doing, which is parents can fill out a personal exemption, right? Personal belief exemption. And California is deciding right now, should we do away with that personal belief exemption? Should that no longer be a possibility? Therefore, effectively requiring you to vaccinate your child. There's a lot of things wrapped up in there, right? That goes simply beyond the science of vaccines are safe. And so it's very touchy, and it's not going to be resolved soon, but needs to be resolved.
So what are the kinds of reasons that people object to vaccination?
Well, one of them is just, the personal autonomy argument, right? That I'll do what I want and no one's going to tell me what to do. Another big one is a major mistrust of the industry. So,
General.
well, it's,
Particular results that they think that they're going to have.
well, that's a third. But the one I was going to mention was, so Big Pharma is in cahoots with the medical establishment to try to make billions of dollars on these products. And if they cause harm to people, well, that's business, right? Which, if you think about it, is fairly ludicrous. because that doesn't make good business sense. But that's one reason. And the other is people have been convinced that from just faulty data that vaccines cause harm, right? And they're not willing to or able to understand the way in which science has said vaccines enormously, if you look at the big picture, are safe, right? So those are three reasons why, you've kind of got this entrenched. So really what it started, and many of you might know this story, that about 20 years ago, there was a researcher who published a paper, a peer-reviewed paper in the scientific literature that had a link between the measles vaccine and the development of autism, okay? And from that point, it exploded. Now, since that time, that paper has been retracted. That researcher lost his medical license for basically scientific fraud. And so it has been thoroughly debunked, and there have been study after study after study that have backed up the fact that that original study simply was wrong. But you get a few vocal individuals, and there's been some celebrity endorsements of this, and you have social media playing into it, and there you go, right? And it gets entrenched, and it's really hard to bring people back out of that. Yeah. Mark.
Dave, I'm assuming your stats that you gave us were for the United States, right?
Which stats were those?
The ones about the increase of cases, or are they worldwide stats?
Oh, yeah, that's the U.S., correct.
How does it compare worldwide?
It's similar. Yeah, Europe is similar. Yeah.
What about like Africa?
Great question. Actually, I don't know. Yeah. So,
Are there regions of the world where this is a more substantial problem than the United States?
the answer to that is probably yes, but they have other diseases that kind of get the limelight. So Africa, whooping cough is just not one of those diseases that is a principal cause of death, because there are others, mainly diarrheal diseases and tropical diseases that are killing children much more than whooping cough is. And so if it is endemic to those areas, it simply isn't getting the attention because other diseases simply take its place in importance. Yeah.
I live in this world, I get vaccines every day as a nurse, but I'm wondering, and a lot of them are to travelers, I'm wondering in the industrialized nations like Northern Europe, Australia and so forth, do they have the same anti-vaxxer groups to the extent that we do?
Yes, absolutely. Yeah. So in fact, in Australia, there was a whole movement that was started with Gardasil, which is the HPV vaccine. So there was a case there where someone claimed that the HPV vaccine, this is the one you get against human papillomavirus, which actually is one of the first anti-cancer vaccines. It actually protects against that particular virus that can lead to cancer of the female reproductive system. There was a case where they tried to link that vaccine to some ovarian problem that led to the dysfunction of the ovaries. And so that took off from there in Australia, and now we had another case. Now I know it's measles and autism, and now it's the Gardasil vaccine and this problem with the female reproductive system. There's been 67 million cases of Gardasil, doses of Gardasil given across the world in the last 10 plus years, and it is extremely well tolerated, and there have been studies that have shown that there is no causal link that was claimed. So yes, to answer your question is there are other places where these claims are being made and have subsequently been shown to not have a causal link between them. And again, that's not to say that when we say vaccines are safe, we're not claiming that there is never any cases where there's an adverse reaction that is medically serious. There's risk in all parts of life. You get in your car and you drive home, there's a risk in driving your car. So when we say vaccines are safe, what scientists are saying, and you probably know this as well as I do, is that if you look at statistically, there is no difference in the development of whatever disease you want to link to the vaccine from those that take it than from the public that haven't had the vaccine. No statistical difference, right? So there is no causal link between the vaccine and that disease. Yes, sir.
In advertising for yogurt and other things, there's a lot of discussion about probiotics
Yeah.
and beneficial bacteria. I was
Right.
wondering, I don't know much more than that. Have there been discoveries in recent years of beneficial bacteria?
Yeah, it's a great question. So the whole probiotic movement might be legitimate and it might not. So there's probably a lot of hoopla going on with the probiotic movement. But what is known is that, so what we're really talking about here, and I mentioned this at the very beginning, are the millions of bacteria that live in your large intestine, right? Those are your gut microflora. And those are amazing research being done with them. We thought that for many, many years, we had thought that they just lived in your large intestine, give you some slight benefit, your immune system tolerated them, and all was well. It turns out that those bacteria in your large intestine are required for your immune system to develop properly. And people have actually even linked different types of bacteria, because everyone has a different set of bacteria. There's some similarities, but everyone has a unique fingerprint of the bacteria that are in their large intestine, and they might actually be involved with neurological development, personality, behavior. So there have been these really outstanding studies that have been done that's saying, hey, we might be at the tip of the iceberg, understanding exactly what these bacteria, these commensal bacteria in our large intestine are actually doing. And so what is known is that you might have heard of the disease C. diff, which is a hospital-acquired infection. It's actually a pretty Clostridium difficile. It's a bacteria that can cause colitis and some really nasty diarrheal diseases. It's a hospital-acquired infection, and what people have actually shown is that you can cure somebody of that infection, this is not very pretty, by a fecal transplant. So you can actually, in feces, which is a lot of that is your large intestine bacteria, if that is administered to someone who has C. diff, the commensal bacteria from person 1 overtakes all of those bad bacteria that's in person number 2. It can cure the disease. So a lot of amazing things that are going on with the commensal bacteria. Probiotics, kind of as a marketing thing, I'm not so sure. But
Steve, it sounds like, though, we need to take care of those bacteria in our large intestines.
you do, yeah, and you know the worst thing you can do, ironically, for the bacteria in your large intestine is take antibiotics, right? Because you take antibiotics, and not only are you killing what you want to kill, but you're killing all your friends in your large intestine. Now, you don't kill them outright and they're gone. They'll replenish themselves, but actually, studies have shown that they might replenish themselves in a different combination than they did before you took antibiotics. And the implications of that are not really well understood.
So when you take antibiotics for a bacterial infection, you don't completely exterminate the bacteria from the body, or it just depends?
Are we talking about the bacteria that are in your large intestine or the one you're trying to get rid of?
Either.
So usually neither. So what you're doing with antibiotics is you're trying to buy time for your immune system. Some antibiotics kill pathogens. We're talking bacteria here. So antibiotics are useful against bacteria. So some antibiotics kill bacteria outright. Okay? Many antibiotics simply keep bacteria from growing effectively wherever they happen to be in the body, and that's buying time for your immune system to kick into gear to take care of it. So when you get sick from an infection, it's from one of two reasons. Reason number one is that bacteria or whatever pathogen is so good at doing what it does that your immune system kind of goes crazy. And the symptoms you feel when you feel lousy and feel sick, that's actually your immune system just too overactive, causing those symptoms. Okay? So that's reason number one. Reason number two is that the bacteria, when it actually gets into the body, can produce some sort of toxin. I showed you the toxin on Bordetella that can actively kill your cells in the body. And if you start killing your cells, you're not having a very good day, right? So antibiotics are designed to either kill bacteria outright or allow your immune system to get enough time so they can ramp a response against them and naturally clear them out.
But also the amount of antibiotics you take is a factor.
Yeah, so
Normally we give some antibiotics, but
right.
not a whole lot.
It depends on the antibiotic.
Friend
Yeah.
who was given massive doses and he had terrible things. Took him a couple of years.
Well-
less food and that kind of stuff.
Yeah, so there's probably two things going on there. The first is different antibiotics will last inside the body for different amounts of time. It's called the half-life. So you take an antibiotic, and the first thing that happens is your liver says, that ain't supposed to be in here, and so it tries to get it out of your body. So some antibiotics can last long in your bloodstream than others. For those that don't last as long, You just have to take more doses to combat it. So that's the main reason that antibiotics. The other is, what actual infection are you trying to combat, right? And so as you all well know, one of the major problems with antibiotics is resistance, right? So you might try antibiotic 1 and it doesn't work because your bacteria are resistant to the antibiotic, so you try the other one and another one. And for some bacterial infections, we're kind of down to the last resort, antibiotic. So you might have heard of methicillin-resistant Staph aureus, MRSA. That's a bacteria that can cause some serious problems, and for some of those guys, there's one antibiotic left that can treat them. And once that one goes, yeah.
The good news is, though, on that front, because of MRSA and the superbugs that
Yeah.
get so much in the news, just now, within the past few months, there are about 5 brand spanking new antibiotics
That's great.
on the market.
That's great.
So,
Yeah, specifically developed because of MRSA, or just also happen to be effective for MRSA?
particularly for MRSA.
That's great.
And the superbugs.
Yeah,
not
right.
just MRSA,
Yeah.
other difficult to treat infections as well.
Which is great because before then, if I'm remembering correctly, there really hadn't been a brand new antibiotic on the market in like 25 years. Yeah. It's tough to develop them. It takes about 20 years to get it. Actually, remember that last slide with all those arrows? It takes about 15 years to get it through. And biotech companies aren't willing to invest the money for something that might, after 15 years, pass muster. So yeah, it's just not, it doesn't make good business sense for companies to do that, so that's great. Anything else?
Well, thank you, Steve.
Yeah, thanks for coming. Thank you very much.